In today's video, we're going to take a look at uncertainty and error. And the examples provided in this video are adapted from our Cognitive textbook, so Cognitive Higher Level Chemistry. So first of all, we should recap some material that we've learned in grade 9 and 10. So there are two different types of data. Qualitative data is made from observations and it's not from measurements. So they would be describing the qualities of something. So no numbers are involved. So some examples would be just to describe the color, the texture, the luster, and so on. So the physical properties of an atom or a substance. Quantitative data is numerical data and measurements. So every measurement includes some sort of error and uncertainty. And we'll talk about that during this video. So quantitative data might be measuring the time it took for the reaction to complete or the temperature change that occurred. So something that's a number. You can also include quantitative data as counted items. So there are 25 of something. So those, if there's 15 people in our class, that's a counted value. There is no uncertainty there. We know there are 15. But measured data always includes some sort of error and uncertainty. So SI units, standard international units, are measurements that we need to be using when we're recording measurements. So we need to use the standard international units in our IB assessments. They are the universally accepted values in science, and I've included a few here. These were found in our Cognitive textbook, but if you go to section 11.1.1, you'll find another table that has a more exhaustive list of the SI units. So, for instance, length is measured in meters, mass in kilograms, time in seconds, temperature in Kelvin, and so on. So these are the symbols that you would be using and the units that you would be using in your assessments. So your IA, for instance. So there are two different types of error. One of them is called random error and one of them is called systematic error. So we'll take a look at random error first. So random error is when you have slight fluctuations in the room or in your ability to read the scale and so on. So they're rarely identical, even if you're measuring the same thing. You have 3 different people to measure the same length. You might get slightly different reports, and that's just due to natural fluctuations. You can reduce random error by taking several measurements and then finding the average between them. So that is why when we do our investigations, we try to do at least 3 trials to avoid some of those errors. So some examples would be the first one, so a draft or a breeze impacting the mass on a balance. So we always try to control as many of the outside variables as possible, so making sure there isn't a draft, but being in a climate-controlled building in the summer, air conditioning vents could come on and start blowing on your scale, or during the winter, you could have the heating vent do the very same thing. Also, when we're doing an experiment, we can't do it instantaneously, so there may be differences in temperature, humidity, and pressure throughout the day, and that could have an impact on your volume of a gas, for instance. And then finally, human error in reading values. We just may make an error. So when we take measurements, we need to report the uncertainty of the device. So we report measured values with a range of uncertainty. So an analog device, so that would be a graduated cylinder, something that doesn't give a digital output. A voltmeter would be another example because that has an analog scale as well. They have an uncertainty of plus or minus 1/2 of the smallest scale value. So in this example, we can see that we have 40.2 milliliters, or 42 milliliters, sorry. So 42 milliliters, but there's an uncertainty of plus or minus 1/2 milliliter. So the way you would record that you would take the guess. So we say it's right on 42, and then we say that the uncertainty is 0.5 milliliters plus or minus. So we're stating that our measurement might range anywhere from 41.5 to 42.5 milliliters. So one rule of thumb is that you always report your uncertainty and your measured value in the same number of decimal places. So if the uncertainty is plus or minus 0.5 milliliters, then we need to report our volume as 42.0 milliliters. And the units will match. So you can include a milliliter here, but because of this, we don't need to. Systematic errors, on the other hand, are consistently inaccurate. So that could be because your device isn't calibrated. So if you're using a sensor, maybe you didn't take the time to calibrate it. Or the experimenter is consistently misreading the measurement. For instance, if you're reading the meniscus of a volume and you're reading at the top, but you consistently always read at the top of the meniscus, your error is consistently inaccurate. But it's always inaccurate to the same degree, so it's not a huge deal. Some examples would be heat loss to the environment. So consistently, some of your temperature is being lost, some of your heat is being lost in the environment. So that is a systematic error. And then also forgetting to zero the balance might be an example. So you put your measuring cup onto the balance and then you forget to zero it, and then you weigh out your substance. So you actually aren't measuring out the exact portion that you thought you were. These types of errors cannot be improved through multiple measurements, whereas random errors can. Those ones are just issues with your design or your experiment. So in this example here, we have a voltmeter that when it's zeroed out, it's always one notch above zero. So the scale is not zeroed, and that is causing some systematic error. So as I mentioned before, consistently reading the volume from the wrong angle can be an issue. So in this case, the person knows that they need to read from the bottom of the meniscus, but they're not having the meniscus at their eye level. So you need to look right here. If you're looking from above, you may misjudge where the bottom of the meniscus is, or if you're looking from below, the same thing. So the idea is that you should try to get your eye level right across or straight across from the meniscus. But if you're always reading from that angle, at least your measurements are going to be consistently off. This graph illustrates the impact of both systematic and random error. So if you had perfect results in a perfect world, all of your data points would land on the line of best fit. That's not what you're going to see ever. Instead, they're going to be slightly off. So in this example, you have some of them falling above and some of them falling below the line, and then you still would draw that line of best fit. That would represent random error. So those slight natural fluctuations in our experiment. The systematic error, so if your scale wasn't calibrated, your measurements are going to be consistently off. So your line will be higher or lower than the perfect results. So, but they would all be consistently off. So when we conduct an experiment, we need to record the total uncertainty through something we know as error propagation. If all of our measurements were in the same units, you could just add up all the uncertainties together. So absolute uncertainty is the degree of uncertainty of a measurement, so a single measurement, and it is expressed in the same units as the measurement. So in this example, I measured several volumes. Each one had an uncertainty of 0.5 milliliters. And because they're all those measurements are in the same units, the total uncertainty can be calculated by adding them together. So my total uncertainty would be plus or minus 1.5 milliliters. So that's an example of absolute uncertainty. And then with the same units, being able to find the total uncertainty by adding the values together. However, often our measurements are in different units. So I might measure the volume, but I might also measure the time, and I might measure the temperature. All of those units are different, so I'm going to have to convert my absolute uncertainty to a percent uncertainty, and then I can add all the percentage points together. So the way you do that is you take the absolute uncertainty and you divide it by the measured value and multiply by 100%. So in our example here, we are going to figure out our percent uncertainty. So we're going to apply that. So we've got our percent uncertainty is equal to the absolute uncertainty divided by the measured value times 100%. So that is equal to 0.5 milliliters divided by 200.0 milliliters times 100%. And we get a percent uncertainty of 0.25%. So that is our percent uncertainty for this. So usually when we're doing an investigation, we have an expected outcome that we are looking for. So whether that's through stoichiometry, where we've figured out the mass of product that is expected by calculating the yield that we should get, or it could be through comparing to a results or a known value in literature. So percentage error is used to determine how close your experimental data match your expected outcome. So percent error is equal to the experimental value minus the theoretical value divided by the theoretical value times 100. So we'll go through an example in just one moment. So here's our example. Air is in a mixture containing 407.4 parts per million of carbon dioxide. A student used a carbon dioxide sensor to determine the carbon dioxide content in the air, received a reading of 425.5 parts per million. Calculate the percentage error. So we're going to find our percentage error. So it's equal to the experimental value minus the theoretical value divided by the theoretical value times 100. So our experimental value was 425.5 parts per million, and we subtract the 407.4 parts per million, divide that by 407.4 parts per million, and times that by 100. So we'll do that calculation. 425.5 minus 407.4, and we divide that by 407.4, and we times by 100, and we get a percentage error of 4.44%, meaning that our measured value is 4.44% off of the expected value.